2 hours after your last meal, when digestion has finished and the small intestine is empty, something begins. A wave of electrical activity starts at the bottom of the stomach, at the pylorus, and moves downward through the full length of the small intestine, the duodenum, the jejunum, the ileum, a coordinated muscular contraction that sweeps everything in front of it toward the colon. Bacteria that drifted up from the large intestine, undigested fragments of food, dead epithelial cells shed from the intestinal lining, mucus carrying the day's accumulated debris, all of it pushed systematically downward in a wave that takes approximately 90 minutes to complete its full transit from stomach to cecum. This is the migrating motor complex, and it has been operating in your gut for your entire life. You have never felt it directly. It produces no sensation you would identify as significant. Occasionally, late in the evening when the cycle has been running uninterrupted, you hear it, the gurgling sound that people sometimes call a growling stomach, which is not hunger but the audible turbulence of a high-amplitude contraction propelling the last of the intestinal contents through an empty tube. Your gut is not simply digesting when you eat and resting when you do not. When you do not eat, it is cleaning. The migrating motor complex was formally characterized by Joseph Code and James Marlett at the Mayo Clinic in the 1970s, with subsequent work by Enteric and colleagues establishing its neurological control pathways. Code and Marlett's manometric studies, measuring pressure waves throughout the small intestine simultaneously using arrays of pressure sensors, showed that the complex operates in 3 phases. Phase 1 is quiescence, no contractions, the intestine at rest. Phase 2 is irregular contractions of increasing amplitude. Phase 3 is the active front, sometimes called the housekeeper wave, a sustained period of high amplitude, coordinated contractions that move at a speed of approximately 5 centimeters per minute down the full length of the small intestine, taking 90 minutes to travel from the gastric antrum to the terminal ileum. Then the cycle repeats, phase 1 again, phase 2, phase 3. Every 90 to 120 minutes, cycling continuously through the night and through any waking period when food is absent. The cycle stops the moment food arrives. Within minutes of ingesting a meal, the enteric nervous system detects nutrients in the lumen, hormones including cholecystokinin and glucose-dependent insulinotropic peptide are released from enteroendocrine cells in the intestinal lining, and the migrating motor complex is suspended. The gut shifts from its cleaning mode into its processing mode. The segmental contractions and peristaltic waves that mix food with digestive enzymes, absorb nutrients, and move the digested bolus forward at the pace required for absorption rather than the faster pace of the housekeeper sweep. As long as nutrients are present in the small intestine, the migrating motor complex does not resume. In a person who eats 3 meals per day with snacks between them, each meal suspends the complex for 3 to 5 hours. A morning snack at 10 a.m., lunch at 1 p.m., an afternoon snack at 3:30 p.m., dinner at 7 p.m., and an after-dinner dessert at 9 p.m. leaves the small intestine running in processing mode from approximately 8 a.m. until 11 p.m. 15 hours, during which the housekeeper wave never completes a single full sweep. The debris that accumulated during the day remains in the small intestine overnight. Or would, except that most people's overnight fast is the only window the complex gets to work. In people who eat late, sleep immediately after dinner, or consume anything with caloric content in the early morning before the night's cleaning cycle has completed, even this window is compressed or eliminated. The housekeeper never finishes the job, and the consequences of an unclean small intestine build across months and years in ways that do not announce themselves as connected to eating frequency until the downstream effects become impossible to ignore. If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. The small intestine is 6 to 7 meters long in an adult and hosts a bacterial population of approximately 10,000 to 100,000 organisms per milliliter of intestinal content. This is a sparse population by design. The colon hosts bacterial concentrations a billion times higher, approximately 100 billion organisms per milliliter. The small intestine is supposed to be nearly sterile by colonic standards, its sparse bacterial community kept in check by several mechanisms. The flow of intestinal content propelled by peristalsis, the bacteriostatic effect of bile acids that reach highest concentration in the duodenum and proximal jejunum, the immunological activity of secretory IgA produced by plasma cells in the intestinal lamina propria, and the migrating motor complex itself, which prevents bacteria from establishing stable colonies by periodically flushing the lumen. When the migrating motor complex is chronically suppressed by continuous eating, the flushing mechanism fails. Bacteria that migrate upward from the colon are not swept back down. Populations that should remain transient establish residence. The bacterial density in the small intestine rises from its normal sparse level toward concentrations that encroach on colonic territory. This condition is called small intestinal bacterial overgrowth, abbreviated SIBO. It was historically considered rare, associated primarily with anatomical abnormalities of the gut, motility disorders, or the use of proton pump inhibitors that reduce gastric acid. The prevalence estimates have shifted substantially as measurement techniques improved. Studies using jejunal aspirate culture, the gold standard diagnostic approach, involving direct sampling of intestinal fluid through an endoscope, now suggest prevalence rates of 15 to 35% in general populations when sensitive culture thresholds are applied, with higher rates in older adults and in people with functional gut symptoms. Mark Pimentel at Cedars-Sinai Medical Center, whose research group has published extensively on SIBO pathophysiology, has proposed that many cases of irritable bowel syndrome, affecting approximately 11% of the global population, represent undiagnosed or inadequately treated small intestinal bacterial overgrowth. His group's data showed that a positive lactulose hydrogen breath test, the most accessible clinical marker of bacterial overgrowth in the small intestine, was present in approximately 84% of IBS patients, compared to approximately 20% of controls in one published cohort. The mechanism connecting bacterial overgrowth to symptoms runs through fermentation. Bacteria in the small intestine ferment carbohydrates that were intended for absorption. The undigested short-chain carbohydrates that should pass intact to the colon, where colonic bacteria are equipped to ferment them, are instead attacked by misplaced small intestinal bacteria. The fermentation produces hydrogen and methane gas in a location, the small intestine, not designed to handle gas volumes. Bloating, distension, cramping, and altered transit time follow directly from the physics of gas production in a structure whose diameter is measured in centimeters. Beyond the symptomatic consequences, the metabolic products of ectopic bacterial fermentation in the small intestine include endotoxins, lipopolysaccharide fragments from gram-negative bacterial cell walls that breach the intestinal barrier and enter portal circulation. The liver intercepts much of this endotoxin load, but chronic low-level endotoxemia from persistent small intestinal bacterial overgrowth is a documented contributor to hepatic inflammation, metabolic dysfunction, and the systemic low-grade inflammatory state that underlies a range of chronic conditions, from insulin resistance to cognitive decline. All of it potentially originating from a cleaning cycle that was suppressed by eating too frequently. The intestinal epithelium is the single-cell thick layer lining the inner surface of the gut. It is one of the most rapidly renewing tissues in the body. The cells, called enterocytes, survive for only 3 to 5 days before being shed into the intestinal lumen and replaced from intestinal stem cells located in the crypts of Lieberkühn, the flask-shaped invaginations between the villous projections of the intestinal wall. This rapid turnover is not incidental. The enterocytes are continuously exposed to an extreme chemical environment, digestive enzymes, bile acids, stomach acid, bacterial products, and the mechanical forces of intestinal content moving across their surfaces. Rapid renewal allows damaged cells to be shed before they fail catastrophically and replaced with functional new cells from the stem cell pool. The renewal process depends on specific conditions in the intestinal environment. The intestinal stem cells that produce new enterocytes are regulated by a complex of signaling pathways, including Wnt, Notch, and epidermal growth factor receptor signaling, and their proliferative activity is modulated by the nutritional state of the gut. What has emerged from research since the early 2000s is that fasting periods, specifically the periods when the intestinal lumen is empty and the migrating motor complex is running, are times of enhanced intestinal stem cell activity. Ömer Yilmaz at MIT, whose research on intestinal stem cell biology and fasting has been published in Cell Stem Cell, showed in both mouse models and human intestinal organoid studies that fasting enhanced the regenerative capacity of intestinal stem cells. The mechanism involves the metabolic shift from glucose oxidation to fatty acid oxidation during fasting, the same shift that drives ketone production in liver and muscle, which activates peroxisome proliferator activated receptor delta signaling in intestinal stem cells and increases their capacity to regenerate the epithelium. In practical terms, the intestinal lining repairs itself more effectively during fasting than during fed states. The stem cells that produce new enterocytes are more active, more capable, and producing higher quality progeny when the gut is empty than when it is processing food. This finding inverts the intuitive assumption that feeding the body supports gut health while fasting deprives it. At the cellular level of the intestinal epithelium, the opposite is true. The lining is being actively restored during the periods when you are not eating, and that restoration is impaired when those periods are abbreviated or eliminated by continuous eating. The practical consequence is that in people who eat across a 16-hour window each day with minimal fasting time, the intestinal epithelium's renewal occurs predominantly during the compressed overnight fast, which may be insufficient for complete restoration of the mucosal barrier. The tight junctions between enterocytes, the molecular clasps that prevent bacteria and bacterial products from passing between cells into the underlying tissue, are maintained by active cellular processes that require the stem cell renewal to proceed adequately. A lining whose stem cells are never given their full regenerative window is a lining whose tight junctions are progressively less well maintained. Increased intestinal permeability, colloquially called leaky gut, is the clinical consequence of inadequate tight junction maintenance. The term describes a measurable increase in the passage of bacterial products, antigens, and macromolecules from the intestinal lumen into the underlying lamina propria and then into systemic circulation. It is measured clinically by lactulose-mannitol ratio tests that track how much of an orally administered large molecule reaches the urine, a molecule that should not cross an intact epithelium. Elevated intestinal permeability has been documented in association with inflammatory bowel disease, celiac disease, type 1 diabetes, rheumatoid arthritis, and a range of other conditions where immune activation at intestinal surfaces is implicated in pathogenesis. The eating pattern that suppresses the migrating motor complex is the same pattern that compresses the fasting window during which intestinal stem cells perform their most active repair. The gut wall contains approximately 500 million neurons organized into two plexuses: the enteric plexus, which sits between the longitudinal and circular muscle layers and controls gut motility, and the submucosal plexus, which sits between the circular muscle and the mucosa and controls secretion and blood flow. Together, these neurons constitute the enteric nervous system, sometimes called the second brain, because it can operate independently of the central nervous system, processing sensory information from the gut wall and generating coordinated motor responses without any input from the brain or spinal cord. The enteric nervous system controls the migrating motor complex directly. The phase 3 housekeeper wave is generated by enteric neurons in the myenteric plexus that fire in a coordinated sequence, creating the propulsive contraction front that sweeps the small intestine clean. The timing and pattern of this firing is maintained by interstitial cells of Cajal, pacemaker cells, embedded in the muscle layers that generate slow electrical waves, providing the rhythmic foundation on which enteric neurons build their coordinated outputs. Continuous food intake does not leave the enteric nervous system unaffected. Enteric neurons, like neurons everywhere, adapt to the demands placed on them. A gut that spends 15 hours per day in food processing mode and only 9 hours in the fasting state is a gut whose enteric neurons are calibrated to food processing demands. The pacemaker activity of the interstitial cells of Cajal adjusts its outputs based on the predominant signals in the gut environment. Research by Gianrico Farrugia at the Mayo Clinic, whose laboratory has studied interstitial cells of Cajal across decades of published work, established that these pacemaker cells are sensitive to oxidative stress, to inflammatory cytokines, and to the metabolic products of intestinal bacterial activity. In conditions of sustained intestinal inflammation or oxidative stress, both of which are consequences of chronic bacterial overgrowth, the density and function of interstitial cells of Cajal are impaired. The slow waves they generate become irregular. The coordinated output of the myenteric plexus loses its precision. The migrating motor complex, already suppressed by continuous eating, becomes additionally impaired by the enteric neuron dysfunction that the suppression has caused. This creates a self-reinforcing deterioration. Continuous eating suppresses the migrating motor complex, which allows bacterial overgrowth, which produces inflammatory mediators, and oxidative stress, which impairs the interstitial cells of Cajal, which makes the migrating motor complex even less capable of running cleanly when fasting does occur. Michael Camilleri at the Mayo Clinic, one of the most published researchers in clinical gastroenterology, has described the functional consequences of impaired migrating motor complex activity in terms that align directly with the most common gastrointestinal complaints in general populations: bloating, postprandial discomfort, irregular bowel habits, early satiety, and the vague abdominal unease that most people attribute to dietary choices, when the actual cause may be a motility pattern that has drifted from its designed operating mode. The enteric nervous system is trainable in the same direction as any neural system. It calibrates to the demands it consistently receives. A gut that is consistently given fasting periods long enough to complete the migrating motor complex cycle has an enteric nervous system calibrated to run that cycle efficiently. A gut that is never given that window has an enteric nervous system that has partially lost the programming. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. The gut microbiome is not a static community. It is a dynamic ecosystem whose composition shifts in response to substrate availability, transit time, pH, bile acid concentration, and the immunological environment of the gut, all of which are influenced by eating patterns. The specific microbiome shift associated with suppressed migrating motor complex activity has been characterized in research using gotobiotic mouse models and human cohort studies linking meal timing to microbiome composition. The pattern is consistent. When the migrating motor complex is chronically suppressed and bacterial overgrowth develops in the small intestine, the colonic microbiome is simultaneously altered in a specific direction. Species that thrive in a food-rich, high-transit environment, primarily firmicutes, expand relative to species that require the chemical environment of the mucus layer and are more dependent on gut wall proximity, primarily Bacteroidetes and Akkermansia mucinifila. This shift in the firmicutes to Bacteroidetes ratio has been associated with obesity, insulin resistance, and metabolic syndrome in multiple independent population studies, beginning with Gordon and Lay's landmark work at Washington University published in Nature in 2006, which showed the ratio was directly transferable between germ-free mice. Implanting the obese microbiome into germ-free mice caused them to gain fat from identical diets compared to mice receiving the lean microbiome. Akkermansia mucinifila occupies a particularly important position in this story. This gram-negative bacterium colonizes the mucus layer of the colon specifically, where it feeds on mucin, the glycoprotein that forms the structural scaffold of the protective mucus layer. This sounds counterproductive, but Akkermansia's activity on the mucus layer stimulates continuous production of fresh mucus by the goblet cells, maintaining mucus layer thickness and quality. In mouse models and human observational studies, Akkermansia abundance is inversely correlated with intestinal permeability, metabolic dysfunction, and inflammatory marker levels. Patrice Cani at the Université Catholique de Louvain has published extensively on Akkermansia biology and shown that reduced abundance, observed in association with high-fat, continuous eating dietary patterns, correlates with increased intestinal permeability and elevated plasma lipopolysaccharide levels, the endotoxin marker that signals bacterial product leakage from the gut. The connection to meal frequency specifically runs through mucus layer quality. The mucus layer is renewed continuously, and its renewal is partly driven by the mechanical stimulation of the migrating motor complex sweeping across the intestinal wall during fasting. Chronic suppression of the complex reduces this stimulation. Goblet cell secretion, which is partly responsive to the mechanical signals of the migrating motor complex contractions, falls below the rate needed to maintain full mucus layer thickness. Akkermansia, finding a thinner substrate, declines in abundance. Intestinal permeability increases. The endotoxin load reaching the liver rises. The microbiome shift is not primarily a consequence of what you eat. It is a consequence of when and how often, specifically, whether the fasting intervals that allow the migrating motor complex to run are present or absent. The most direct evidence for restoring migrating motor complex function comes from clinical studies of small intestinal bacterial overgrowth treatment and from intermittent fasting research that has measured gut motility outcomes rather than only metabolic or weight outcomes. Pimentel's group at Cedars-Sinai has published data showing that successful treatment of SIBO, whether through antibiotics, elemental diets, or dietary modification, produces measurable improvements in migrating motor complex activity when assessed manometrically before and after treatment. The finding establishes bidirectionality. Suppressed migrating motor complex allows bacterial overgrowth. Reducing bacterial overgrowth restores migrating motor complex function. The question is which intervention to apply first, and the dietary evidence suggests that restoring the fasting window provides the migrating motor complex the opportunity to prevent bacterial accumulation before pharmacological treatment becomes necessary. The dietary intermittent fasting literature has grown substantially since 2015, and several gut-specific studies within this literature have measured outcomes beyond weight and metabolic markers. Morrow and colleagues, whose 2016 study in the Journal of Translational Medicine examined time-restricted feeding in resistance-trained athletes over 8 weeks, found not only the expected metabolic improvements, but also reductions in inflammatory markers, including interleukin-6 and tumor necrosis factor alpha, inflammatory cytokines, whose elevation is associated with intestinal barrier disruption, and whose reduction is consistent with improved gut barrier function. Sutton and colleagues at the University of Alabama published data in Cell Metabolism in 2018 showing that a 5-week time-restricted eating intervention in metabolic syndrome patients produced improvements in insulin sensitivity, blood pressure, and oxidative stress markers without caloric restriction. The eating window was compressed without reducing total food intake. The gut motility implications were not directly measured in this study, but the improvements in systemic inflammation and metabolic markers are consistent with reduced endotoxemia from an improved gut barrier. The most gut-specific evidence for the benefits of restoring fasting windows comes from Sachin Panda's laboratory at the Salk Institute, whose time-restricted feeding research in mouse models has shown direct effects on the gut microbiome, the intestinal barrier, and the circadian clock genes expressed in the intestinal epithelium. Published work from Panda's group demonstrated that time-restricted feeding synchronized the circadian expression of clock genes in the intestinal epithelium, reduced intestinal permeability, and altered the microbiome composition toward greater diversity and higher Akkermansia abundance compared to ad libitum eating of identical food quantities. The translation from mouse models to humans is not always direct, but the circadian biology of the intestinal epithelium is conserved across mammals, and the mechanistic basis of the findings, the alignment of the fasting window with the natural circadian rhythm of gut motility, which favors migrating motor complex activity during the dark phase in nocturnal animals and during the overnight period in humans, is directly applicable. The migrating motor complex requires a minimum uninterrupted fasting period to complete a full cycle. A single phase 3 sweep takes 90 minutes to complete its transit from gastric antrum to ileum. but the preceding phases I and II together require another 30 to 60 minutes. A full cycle from the initiation of Phase 1 to the completion of Phase 3 takes approximately 2 to 2.5 hours. To run 3 complete cycles in a single overnight period, sufficient to clear the small intestine comprehensively, requires a fasting window of at least 6 to 7 hours. To additionally allow for the digestive clearing of the previous evening's meal before the migrating motor complex begins, which typically requires 2 to 3 hours after a standard dinner, the total overnight fasting window needed to achieve 3 complete sweeps is 9 to 10 hours minimum. This maps directly onto the fasting window achieved by finishing the last meal by 7 to 8 p.m. and eating nothing until 7 to 9 a.m. the following morning. The total opportunity window is 12 to 14 hours. Subtracting the 2 to 3 hours of post-dinner digestion before the complex initiates, the actual migrating motor complex runtime is 9 to 11 hours, enough for 4 to 5 complete cycles. This is the specific reason why a 12 to 14-hour overnight fast is the minimum threshold that shows measurable gut-specific benefits in the research, as distinct from the metabolic and weight-related benefits that may require longer windows. The gut benefits are not primarily a function of caloric restriction or ketogenesis. They are a function of whether the migrating motor complex received enough uninterrupted time to complete its work. The 21-day timeline for observable changes is layered by mechanism, and each layer has a different pace. In the first 3 to 5 days of consistent 12 to 14-hour overnight fasting, the most immediately measurable change is in bowel transit consistency. The migrating motor complex is running for the first time in weeks or months with adequate time to complete its cycles, and the sweep of accumulated debris from the small intestine into the colon produces transit patterns that may initially be more active than the person is accustomed to. This is not pathological. It is the mechanical consequence of the housekeeper finally finishing its job. By day 7 to 10, the bloating and postprandial distension that many people attribute to food intolerances frequently begins to reduce. The bacterial overgrowth in the small intestine, deprived of its continuous substrate and increasingly cleared by nightly sweeps, starts to decline in density. The fermentation of carbohydrates in the wrong location decreases. The hydrogen and methane gas production that caused the distension falls. By day 14 to 17, mucosal barrier integrity begins to improve as the intestinal stem cells are consistently receiving their full fasting window enhancement of regenerative capacity. New enterocyte cohorts produced under these conditions maintain tighter tight junctions than their predecessors produced under compressed fasting conditions. Intestinal permeability, which would require a clinical test to measure directly, is moving in the right direction by signals the person may notice indirectly. Reduced systemic inflammatory symptoms, reduced post-meal fatigue, improved skin clarity, all consistent with reduced endotoxemia from an improving gut barrier. By day 21, the microbiome has begun its compositional shift. Akkermansia muciniphila, which responds relatively rapidly to changes in the gut environment, begins to recover toward higher abundance as the mucus layer thickens from improved goblet cell secretion, stimulated by the recovering migrating motor complex activity. The firmicutes to bacteroidetes ratio begins moving toward a more favorable balance. The enteric nervous system recalibration is the slowest component. Neural adaptation in the enteric plexuses occurs over weeks to months rather than days, and the interstitial cells of Cajal, whose function was impaired by chronic bacterial overgrowth-associated oxidative stress, recover as the bacterial overgrowth itself resolves. The full neurological restoration of the migrating motor complex's coordination may require 6 to 12 weeks of consistent practice, rather than 21 days. The protocol is simpler than its mechanism suggests. Finish eating by 7 to 8 p.m. Consume nothing caloric before 7 to 9 a.m. Water, plain tea, and black coffee do not trigger the hormonal responses that suspend the migrating motor complex. They are safe during the fasting window. Do this on at least 5 of 7 days per week, consistently enough that the gut's enteric programming recalibrates toward the fasting window as a reliable daily event. Conterec's early research on the migrating motor complex established that the complex develops stronger, more regular phase 3 sweeps in subjects with consistent meal timing than in those with irregular patterns. The gut is a biological clock operating on the same circadian principles as the rest of the body, and like all circadian systems, it performs best when its inputs arrive at predictable times. The habit that is missing is not a supplement. It is not a dietary restriction or a specific food. It is an interval, a window of absence that the gut has been designed to use for its own maintenance for the entire history of the species, a window that modern eating patterns have compressed until the housekeeper has nowhere to work. Give the gut back its window. The cleaning cycle was always there. It was simply waiting for the space to run. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.